There's a little lag. There's a little lag. Okay, there we go. So again, thanks very much for the opportunity to be here. As Dan said, a lot of what we've been thinking about in response to what we heard, was going on, particularly during the heat wave in June, kind of comes down to a variety of topics involving groundwater supply management. And so what we thought we'd do today is start off a little bit with talking about groundwater models, partly because that's what I do, and some of their readiness for modern day needs. I'm getting involved in a lot of projects up and down the West Coast where the common theme seems to be, how do we make sure our water systems are resilient, given some of the changes we're seeing, whether it's natural and in the watersheds and climate related, to what extent it's demand driven, even regulatory driven, that kind of thing. And so we'll talk a little bit about groundwater models and how they can help with thinking about wellfield and water supply operations, as well as a little bit about just what it means for long-term planning. Wellfield operations are both a long-term and an immediate need to be thinking about at times. But there's also kind of long-term management of the aquifer and your systems as well. And there's times when models can help with understanding those things. A part that Kenny will talk quite a bit about, one of his specialty areas, is in well performance maintenance and rehabilitation, because obviously, if the system is starting to get used as hard as we heard the system was recently, that's going to be one of the first places you're looking at what you have and how it's performing is in that area. So he'll talk about that. And then Dan will finish by talking a little bit about coordinated water conservation planning, including some of the things, skill sets that we have inside GSI, where we've helped a few other clients in this area. Let me talk just a little bit about groundwater models without turning into a groundwater model geek. I'll try really hard not to do that. Why do we use groundwater models, which are models of aquifer systems and of how wells and other features in the aquifer work? When I think about, I've been doing this for 30 years, in fact, longer than that. When I think about why have people asked me to do this and why do they keep paying me, which is a great thing, it kind of comes down to, number one, wellfield operations and wellfield management. There are utilities out there really thinking hard about how do they optimize the operations of all their assets. And oftentimes you're talking multiple wells. I'll give you an example from Portland a little later. Siting and designing new wells. We've been doing a lot of that kind of work lately, which I've been a little amazed at how much we've been doing. And give you some insights as to how models with that. And along the way, the models often help us understand how the aquifer behaves and what effects the aquifer is having on how wells and well fields are going to perform. So we build models a lot around with that water supply management optimization concept in mind. There are other factors too. If you think about the operational effects of changing water demands, the amounts of water use, like you were just describing, Terry, the timing at which maybe you have to run a system, at or near your, peak season rates. Some of those can change over time for various reasons, whether it's maybe climate change driven, demand driven. We use models to sometimes look at effects of climate change on an aquifer system. And if there's an interconnected river system, I'm surprised how many of the models I'm doing nowadays are examining groundwater surface water interactions, whether it's water rights related or in California, I'm doing a bunch of work that's related to protecting habitat. And the models are playing an important role down there. And then lastly, particularly on the Washington side, a lot of attention's been paid to pumping effects on the river, and that's revolved around water rights and in-stream flow questions. So let me talk first a little bit about the wellfield operations and how models can help. And I'm going to start by showing you some examples of the models that have been built out here in this area. The very first model that I know of was a model that looked like this, built by the USGS in the early 1980s. And this was back at a time when the USGS didn't even have a standard groundwater modeling code yet. They were actually working to develop one, which they released a few years later, called ModFlow, you might have heard of. But they built a model that tried to represent the aquifer system, mostly on the Washington side, extending a little into Idaho, very coarse grid. Mostly it was a model they were using at the time to think about some of the issues around water quality in Spokane County and the issues with chloride and nitrates in groundwater because of the prevalence of septic systems out there. And there wasn't a whole lot of detail about the groundwater flow system. That's actually a map we're looking at. So you can tell it was pretty darn coarse in terms of, what it could look at. The next model that came along was one that I really got my time up here in the region going. It was back in the mid 1990s, culminating in 1998 with a report that was for wellhead protection, initially for the city of Spokane, later also for the Spokane Aquifer Joint Board. And I'm sorry, probably not showing up real well, but if you look around the city's wells that you see there, these little clusters of dots, and this was a model that actually came out of Europe that we found really good for being able to simulate a regional flow field, but zoom in on a local area of interest, such as around a well or along a river. And we were able to do a lot with that model and actually still have in recent years. About 10 years later, the USGS came along and built the bi-state model, which some of you may be familiar with, that covered the entire Spokane Valley, Rathdrum, Prairie aquifer system from Lake Pend Oreille all the way down to Long Lake. As you can tell in this model, it was using square grids. And again, they're fairly coarse. One way you can know it's coarse is because I'm trying to show a grid and it's not just all a big black blob. You can see white space in between. Kind of helpful for understanding the regional system for sure, especially because it's covering, it covers an area that is the whole entire aquifer footprint. So its boundaries conform to the natural boundaries of the aquifer system. The city and SAJB model actually later got expanded into that same area covered by the USGS model. It had started out as a model that stopped at the state line for various reasons related to wellhead protection being done in Washington, and they didn't want the capture zones extending into Idaho. kind of the reality of it. But later on, as time went on, it was seen that there was a lot of benefit to having a model that, again, covered the entire aquifer system. And some of the benefit can really be seen in this next slide that shows what that benefit is. The USGS model, I've overlain the black square cells, and the little black circles are just the centers of the cells on top of the grid that city SAJB model uses, which is in that light blue. And what you can see right away is that, we were able to build in these, fine meshes around individual wells owned by individual water purveyors and look at the flow fields at a fairly close scale and understand the hydraulics in a way that you just can't do with those larger grid block cells. And if you even if you were to just zoom in on one of those large grid block cells, here's one of CID, one of your wells, the 2A, 2B, 2C well field. I mean, look at what we were able to do there in terms of, refined gridding inside what's a really large quarter-mile by quarter-mile cell in the USGS model. So lots of things that are really great to do, and you could build flexible grids and be able to really do just about any kind of analysis. And so one of the things I've been thinking about lately is that, both tools have served their purposes well over the years, the city SAJB model and the bi-state model, but they're getting kind of long in the tooth, kind of showing their age a little bit. The bi-state model, of course, has a pretty coarse grid. The other thing about it is in most of the area that it's simulating that whole entire thickness of the aquifer with just one model layer. So you cannot model the vertical flow component in a one layer model. You're essentially modeling two-dimensional horizontal flow and not capturing the vertical. So we had all along in the city SHJB model had a minimum 3 layers in that model because we wanted to capture that, you know, most of the wells, particularly in Washington, were only in at the upper 70 to 100 feet of the aquifer, and there was still maybe 300, 400, 500, 600 feet of aquifer beneath that. And when you're starting to think about the dynamics of how a river and an aquifer interact with each other, plus a well, you got to have that three-dimensional aspect to it. The thing about the city SHJB model is the software hasn't really kept up over time. So I don't know if anybody owns an iPhone 1 or an iPhone 2, but we're kind of getting a little bit in that space. Plus what happened recently and very abruptly, the developer of the model retired and I guess gave the rights to the software to some European firm I've never heard of, and I don't know how many people have. So, you know, we can still use it, but I'd say its future is kind of questionable. The good news is some terrific tools I'm about to show you have become available in recent years that are actually through the USGS, but something they've done that they really never used to do was they've partnered with some specialists in the private sector to build some really terrific flexible tools that allow you to embed grids inside a model where you want them, turn them off and on, and really not lose the local detail in your aquifer system or the regional detail while you're simulating the local detail. I'm trying to pull up a graphic. There we go. So here, let me give you some visual examples of that. One of the places I first started using this was down in Prineville, Oregon, where we had built a model maybe 7 years ago, fairly regular grid cells. The green shows where there's some river systems. And we, a couple of years later, started doing some work in one part of this that we wanted to study a little more closely. It was an area called the airport wellfield. So we wanted to build a refined grid in there. And, you know, the thing with the old tools was if you wanted to build a refined grid and focus on an area like right here, you had to carry all these cells out in other directions and just increase your computational burden and costs and everything really badly. Well, look down here, there's a little spot right here where there's a dense blob. And in these new tools, what we can do is start embedding grids wherever we want them and look at questions like a groundwater supply that they actually wanted to develop in that part of the basin to pipe water over to that airport well field to inject for all kinds of different reasons, kind of a complicated project. And so we built that nice little grid. This is a zoomed in view, looking at how we could, you know, really kind of custom design a grid to look at conditions along a river, think about well locations, think about how to optimize the operations of those wells, run simulations that tell us when the model or when the wells are running, what do the groundwater elevations look like? Trying to get that to come up on the screen. There's quite a delay here. And there we go. You'll see a contour map that the high groundwater elevations are in red, the greens and blues are the low. So you can start really simulating in detail right around your area of interest. What does that drawdown cone look like? How deep is it? What's that water level threshold going to mean relative to where I've set a pump or I, you know, have a well screen? And, you know, really zoom in on these things and build in all the detail that you want. It's really a terrific capability. And, you know, we used to spend weeks doing these kinds of things in the old tools, and you can pretty much go outline an area with your mouse, turn it on, and, you know, depending on the model, some are easier than others, but you can get some analyses done real quickly. The other thing, this is an example from a model I've worked with for a long time in Southern California. you can nest these grids inside other nested grids that you build. So in this basin, we had a parent grid covering the whole groundwater basin. We had a sub-regional mesh I call level 2 that was focused along river corridors and alluvial valleys. And we've done all kinds of modeling with that model. Just a few weeks ago, I actually got asked to look at a local project involving an area where they're thinking of installing 2 more wells and trying to pump harder in that area. So we just went and built another local grid right in that spot, turned it on, ran the simulations of the water scenarios they were interested in, and it's helping them with some well designs that they're working on. This one's an example from Redmond, and the city of Redmond has 5 wells in their downtown area. And I wanted to show this one to you because this is a case where we turned on multiple of these grids, all at once around each well field, simulating various things in various ways. And it's been very helpful for them to think about how to manage their groundwater supply, because they have wells that are in their urban core downtown, which the entire downtown, if you've been there, is undergoing just an incredible transformation of land uses. And they've had a lot of concerns about what does that mean for that groundwater system. Let's come back to Spokane. We've done a lot of work for the city in recent years as they started the process to build their first new water supply well in 7 decades, the Havana Street site. And this is a map from that existing model showing again where the city has all their wells and a couple other sites they were thinking about developing, Audubon Park and Faith Bible Church Corbin Park area. But they've done work at Havana Street is where they focus their efforts. And if you look at that, tiny little blob of grid there and blow it up at Havana Street, this is what it looks like. We have done quite a bit of work helping them figure out how much could they pump and how many wells would they need from this parcel of land that they had access to. That wasn't huge. But this aquifer is so crazy permeable, you can actually pump a lot from even a modest parcel of land, as I'm sure you all know. So we did quite a bit of work with first doing a test well installation and pumping that, monitoring water levels in the new monitoring well, and at a observation well that the county's had out there for, now about 20 years. And then we worked inside this area that was identified as the footprint where we could put wells to, really study in detail, how should we lay them out, how should we pump them, et cetera. And of course, it's just a model, so we got to have good field data. We did a 5-day long pumping test of that test well, monitored the observation wells we had, monitored the river and what it was doing, which is that top line. Over here, monitored what was happening before the test started, monitored water levels on this site during the test, and then the recovery and the trends afterwards. We also looked at data at that county observation well for the prior 15, 16 years to think about how during the summer season, which you see circled in the green, some of these lowest year dry summer conditions, to us, that kind of defined the water column that we had to work with in terms of during the summer months when they want to operate that well and that well field, what do we really have to work with? And the number is really astounding that there's shallow bedrock there. And because of the way the well design would work, the shallow bedrock and these low water levels, we have about an 8-foot water column to work with to provide pumping during, for municipal supply. I've never run across that anywhere else. That makes a hydrogeologist's head explode in most places to think about trying to develop a water supply in that environment. That's just how crazy permeable this aquifer is. But we took all those data sets and then we're able to run screening level simulations, well, more than screening level, through the model to say, okay, take those data sets, take that fine model with its local detail, but also its aquifer-wide influences, and start thinking about how could you best lay out that well field in terms of number of wells, target production rate, how much drawdown you're going to get, and whether you're going to have problems meeting the production targets with just that 8 foot of water column, and trying to think about how, it is the subsurface. There is always a little uncertainty down there, and we have to take that into account in our modeling analyses. And so out of all that came the decision to build 6 wells on the site. We figured out a network to arrange them in on the site, and the city was then able to proceed with thinking about how to get those wells in the ground, and then start bidding the engineering services for it. And so the model played a critical role in doing all that work. And I just want to put this up again as a reminder, partly to myself, but all of us, that, a really good locally detailed model can go a long ways in helping us understand how to build a well field and how to run it. Now that all those examples I just showed you were mostly about new wells and well field designs. But I'm going to turn to one that we did back about 3 years ago for the Portland Water Bureau, that was all about optimizing the operation of the assets that they already have. This map, the white area, is showing what's called the Portland Geologic Basin, which has this large aquifer system in it that's basically have a large shallow regional system, and then systems at various different depths further down in the basin. The Water Bureau has its emergency well field along the Columbia River from about I-205 in the Portland Airport, a few miles east of there. And back in 1996, the USGS built really a pretty good model of that entire basin. It was coarse, but it captured everything that needed to be captured there. Starting in about 1999, continuing through 2001, I got asked to work with the lead hydrogeologist at the Water Bureau to take that model and turn it into a well field model with that local resolution. And then in 2014, do further expansion and refinements of it. And in 2018, we really put that thing to some serious use, because they were working on a master plan for their water supply portfolio. And, most of you may know that they're partly dependent on groundwater, but Bull Run, the surface watershed, is their primary supply, federally protected watershed. And what they asked us to do was to look at various demand scenarios in terms of how they would operate the wells over a multi-year basis under those demand scenarios. So this first one, and what you're looking at, are 2 plots. They're for 2 different wells. They both happen to be in the deepest of the aquifer systems. The Bureau actually has water wells in all 3 of their systems, and we looked at them all together. And what we were basically doing was saying, okay, here in the dashed red line is the cutoff level for where that well has to come off if the water level ever drops that deep. And so we had this one well where it was pretty deep, and sorry, something went haywire. And one that's a little shallower. They run their wells usually on a seasonal basis. So during the winter months, they're mostly relying on Bull Run for the water supply. They turn the well fields on in the spring, run them for about 4 or 5 months each year, maybe 6. And that's what you see in terms of the cycling of what are water levels in those wells. The blue water levels were basically accounting for their pumping plus regional pumping around that whole geologic basin. They asked us to run a model without the other folks pumping, which is the orange line, just so they kind of knew how much their contribution was. But at the end of this base demand scenario, they had us run a simulation where they said, oh, and at the end of the summer peaking season, let's assume that we had a major flood event occur in Bull Run, created turbidity problems, and we couldn't use the surface water supply. We have to go on well fields for 100% of the supply for 30 days. What would that look like? And that's what these curves were here. And we could see that this one well it's saying, yeah, the rate you want to pump that one, you may have to back off because you're going to run dangerously close to hitting that cutoff level. This other well here, though, it's got room. Maybe if you're running the model at what you think the capacity of that well is, see if there's something that you can do to maybe increase that capacity a little bit, because you can make that up. They had us run another scenario that they call the wildfire scenario. What if wildfire happens in a large part of that watershed and the turbidity levels are so high that they can't use it? In this case, for 3 years was what they asked us to assume. And those two same wells, you could see they were going to run into problems each summer in this one well, but also the other well, it was going to start getting a little bit nip and tuck. So we did this for all of the 25 or 30 or so wells that they had. And they've said it's been very informative to helping them think about things in the long run. So with that's all kind of a focus on how models help with well field planning. But obviously the on the ground stuff's really important. How are wells operating now? What can we do, to look at that question? And I'm going to turn this over to Kenny Jenssen to talk about that topic.
Thanks, John. Do you just want to save questions to the end, or is there any questions for John on that? No?
Why don't we save them for the end?
Okay, sounds good. All right, so some other water rights and a new source, but they had the question of, hey, we have a couple of these downtown wells that we want to increase the capacity on. What can we do? We want to put some larger pumps in there. We want to pump them a little bit harder, but is that something we can take a look at? And I recommended, well, as long as you're taking out the pumping systems, you might want to have a peek inside just to see what's going on. It may be worthwhile, bailing out or pumping out some of the debris that maybe have settled into the bottom of the well over the years. And these are screenshots from the video that we saw. That upper left corner there is the bottom of the well. You can see some equipment that had fallen in at the bottom. There was a fair amount of sedimentation that had accumulated in the bottom and plugging up the bottom part of the screen. The side views, the 3 other ones, show some pretty serious corrosion on a lot of the rods on the well screen. This is a continuous wire wrap well screen. It's the well's about 50 or 60 years old. And it was pretty heavily encrusted. So a lot of the flow is only coming through a small open area of the screen, and that actually ends up exacerbating a pre-existing problem that you may or may not be aware of, because you're drastically exceeding those fluid entrance velocities, which is causing more corrosion or more precipitation of some mineral incrustations and can compound some problems. So wells for this particular provider, we were able to do some minor rehabilitation, but the age of the well, the condition of the well made us really nervous. We didn't want to brush it too hard. We didn't want to use some abrasive chemicals that could contribute to more of the corrosion and make it fail. So we ended up just doing a really light brushing with the nylon brush instead of a heavy steel brush and being really aggressive. We just took a more subtle approach, and we were able to clean up some of it, but not all of it. But they were able to increase some of the capacity there. But they had no idea about the condition of the well. They were surprised when they saw it, and that just told us that some municipalities, some water providers are really good about tracking and monitoring performance and doing some routine inspections and monitoring to see how that asset is changing over time and whether they need to make any changes. And that's something that we highly recommend, but also understand that communities are different. Some have a big customer base and a large pool of money they can pull from and help, but others operate on a much skinnier budget and don't have that luxury. And it could be a source limitation too, where they can't afford to take that well offline. They need that. That's their only reliable sources of supply. So it can get tricky. And so we try to help them adapt to whatever their needs are. But, wells are not just, holes in the ground with pipes stuck in them. They're more of an engineered a design for highly variable and unseen conditions. We don't know what's down there. Sometimes we can rely on existing well logs or other wells that have been drilled in the area to give us an informed decision about how we would design it and how deep it could go and what slot size we would be able to use to get the most efficiency out of the well. But they're not passive structures. It's kind of like monitoring the oil in your car and changing it regularly to get that extended life that you want out of your vehicle. If you ignore it, well, then the engine life is gonna not take you as far as you want to, and you'll be replacing that vehicle sooner than you would otherwise. So typical life cycle for a production well, I'd say in normal groundwater environments, 40, 50, 60 years. I've worked on wells that have biofouled before they even had a chance to build the facility. If they drill the well, it takes 2 or 3 years for the facility to get permitted and constructed and built and connected. And by that time, there could have been some bacteria that makes its way in there for whatever reason. And, now they have a well rehabilitation plan that they got to implement before even putting the well into production. I've also worked on wells that are over 100 years old and are still functioning today. So there are some outliers there, but typically, 40, 50, 60, 70 years is a typical for most production wells. And the life cycle is, the planning and design portion. Find out where you want to construct it. Where do you need it? Where's some infrastructure? Where do you have land available? Get through the drilling and constructing phase, test it, get it online, and then you're through the operation and maintenance. And then throughout that time, some periodic maintenance and performance monitoring. And you may have to go in and clean it out periodically to optimize the performance and really get the most out of that asset as possible. And then at some point, as it gets older and older, it's harder and harder to maintain. You get a point of diminishing returns, and it just comes to a time where you just need to retire and replace it. And today, I'm just going to focus on the kind of the maintenance and the rehabilitation portions of it. So some of the problems that we typically see, I'll get a call from a client saying, "Hey, my well's not producing like it once was. Well, what's going on?" Well, okay, it could be a variety of things. It could be the pumping system. It could just be old. The impellers might be worn. You could be pumping sand. It's not efficient. It's off the curve. There could be holes in the pump column. It could be leaky. It's not really producing like you would expect it to. It could be the aquifer. It could be declining water levels or seasonally changing water levels, where John had mentioned, the water column, the available drawdown. You want as much available drawdown as you can so that your pumping water level is maintained above your intake. Otherwise, you're going to be sucking air and you're not going to produce anything. Or it could be the well itself. If the screen gets plugged, then it's becoming less efficient. There's more drawdown. It's not producing like it once was. Or it could be a combination of some of these. I've just helped the city of Milwaukee. They are really good about monitoring or looking at doing some routine inspections. And through one well video that they saw, there was an old perforated well casing that the perforations ended up zippering open, and they had sand and gravel coming in, and they realized right away that, we have to shut this down or throttle way back on it and then plan for replacement. So, that is a compounding issue where now it's pumping sand, maybe some gravel, and now you're causing some problems, some wear and tear on your pumping system. So what we'll look at is we'll go out and do a pumping test or a short flow test and see, have you experienced any decreases in your wire to water efficiency? Is there more of an electrical demand? Is it a pumping system problem? We don't necessarily want to take out the pumping system because that's costly. It takes the well offline. We want to see if we can do some diagnoses before getting to that point. So what are some indicators that could help us diagnose the problem without spending a lot of money up front? Have you noticed any groundwater level declines? Is your static water level deeper? You're losing that available drawdown capacity. So when you turn on your pump, as you would normally pump it, that pumping water level could get drawn down past the past your intake and cause it to cavitate? Have you seen any evidence of that? Or have you seen any changes in color or odor? Pulling a transducer out or replacing the batteries on it? Are you noticing slime or any biofilms on the cable or the sensor itself? Or have you noticed a decrease in the performance? And that's the specific capacity is one thing that we track or recommend our clients monitor to give them some sort of early indicator on a decline in the performance of the well, and there might be a problem going on. Specific capacity is the pumping rate divided by the drawdown. So at 500 gallons per minute with 10 feet of drawdown, that particular well performs at 50 gallons per minute per foot. So you have kind of a baseline threshold or baseline where you can compare maybe some recent pumping or from that baseline measure on. How does that compare to that old measurement? Are you seeing some steady declines over time? And at some point, it's not working like you need it to, and it may be time to do some brushing or bailing or swabbing or surging or something to reestablish that hydraulic connection between the aquifer and the well itself. And so that these dips in the curve here would be places where you would rehabilitate the well to get it back up to where it was once performing. But depending on where you catch that loss in performance, if you let it go too long, it's harder and harder to regain that lost performance. So if you were able to catch it earlier on the curve, you could change the projection of that sort of slow death of the well over time and maybe flatten out that curve and get more out of the well over several more years than you otherwise would if you ignore the problem or you're not aware of it, because the longer it goes underperforming, the more difficult it is to rehabilitate it and get it back to where it once was. So that's where the performance monitoring and tracking really becomes important, because the earlier you catch it, the more likely you are to really be able to regain it. So we recommend a proactive approach, monitor and track that performance, do some routine inspections, pull the well or pull the pump periodically, have a look at it. Are there any issues? Do a video survey. Are you noticing any plugging of the screen? Are the slots still in place? Are you noticing any sand or gravel coming in? And if there's any flock or any evidence of slimes or biofilms, we would recommend, taking a groundwater quality sample and sending it in for a microbial assessment, where that would tell us the information that we would need to be able to design a chemical rehabilitation program targeted for whatever iron oxidizing or pathogens or bacteria that may have established in the well. But a lot of the times that's not the case. The purveyors may not have those resources available or the time and the money it takes to do that. And we don't learn about it until the pump is damaged or the well is failing. And at that point, it's a little too late. And there really there is not a sort of a silver bullet solution to well rehabilitation. Every well is different. They come in all shapes and sizes in different geologic environments. They're operated differently. They're constructed of different materials. Their age could be different. The groundwater quality could be different. So you really have to factor that in to developing a rehabilitation program. Like I mentioned, the municipality earlier when we started, we chose deliberately not to do an aggressive chemical and physical rehabilitation program because of the age and the condition of the well. We didn't want to damage it. They needed to use it, but we were able to, balance a little less aggressive approach and break up some of that stuff with keeping the well intact, still functional, and getting them what they needed. So, a common well is a filter packed well where you have your well screen installed, and then it's encased in this envelope of sand, the filter packed sand that acts as kind of a pre-filter before that water enters into the screen. So when we design the screen, we'll design the size of the filter pack to hold back the formation, and then the screen slot size to hold back the filter pack to give it its most optimal and performing ability to really create as much efficiency in the pumping as we can. And that's really, a lot of it's dependent on, the different well screens that are used in wells. This one on the left is a wire wrap continuous. It has the most open area. It'll be the most efficient. Other types are, shutters or louvers, and you can just kind of tell from the picture that the open area is not as much as the wire wrap screen, and even less so than, the perforated well casing is even, less open area. So from a rehabilitation standpoint, getting that energy, imparting that energy out to break up any of the formation or any of the clogging is going to be a little more difficult in the perforated casing than the wire wrap screen, because it's more difficult to get that energy out in the formation to break up anything that may be plastered up against the side of it. There are natural packed wells where you don't need the filter pack. You can just depend on the formation itself. It's well graded, it's sand and gravel, it doesn't have fines. So the ability to do that is great. It saves on construction costs. It saves on well rehabilitation costs because you don't need to get energy out past or through the screen and then out past the filter pack and out into the formation. And it just makes for a more efficient well. You don't have the head losses moving as the fluid moves through the slots and the screen. Hard rock or open borehole wells. This one shows that it's cased down through, cased and sealed to a certain depth. And then it's just open borehole getting water from some of the fractures or joints in bedrock or the Columbia River basalt. Sometimes these wells have a perforated liner in them. It kind of depends on what the performance and the efficiency of the well, where the static water level is. You don't want to hang your pump in the open borehole portion, because if there's ever any caving or rockfall, now your pumping system is trapped down there. They may not be able to get it out, and now you've just lost your well and your pumping system. So under ideal conditions, you could hang your pump up into the case zone where it's protected. Otherwise, if that drawdown, the well is, the specific capacity is low, the performance is low, and your water level is being drawn down further, then we would recommend a liner be installed just to protect your pumping system. Larger wells, collector wells, these are riverbank filtration wells. These are 10, 20 plus feet in diameter, reinforced concrete with lateral well screens that move out horizontally from the bottom. And the picture on the left, you can see there's a couple of guys down in the bottom of this. This is like a hydraulic jacking system. There's a guy here with a yellow safety jacket on and a white hard hat, and he's running this hydraulic jack that pushes these the screens out laterally from the base of the collector well. And then the Caisson Wells are similar. The city of Spokane has a number of them. Taking a second while the picture loads. These are very similar to collector wells. They don't have the radial well screens, but the pictures on the right are from the well electric, a couple of the well electric Caisson wells that were drilled. These are like 40 feet in diameter, 40 to 60, 80 feet deep. No screens, just open to the sand and gravel below. Very high producing, very efficient, very productive. The one on the left is the Hoffman well. That's brick lined, 6 to 8 feet in diameter up top, goes to maybe 12 to 16 feet at the bottom. That's like 200 feet deep, another big high producing well. So you can kind of see the different well types are going to dictate what sort of rehabilitation or restoration strategy you need to do. The collector well, you're probably going to need to send divers down in there to actually do the work. And a smaller, more traditional vertical 12-inch diameter well, there's some tooling that can be used to help with the rehabilitation. So let's say you have a problem, the well's not performing as you expected, now what? Well, you can do nothing and hope for the best, which we don't recommend. Diagnosing and preparing a targeted plan to repair or restore it, manage and protect your asset is what we would recommend. Or, hey, if this well has been problematic, you're having to rehab it more and more frequently, you may be coming to a point where, hey, we're tired of throwing money down this well. Let's just look at locating or replacing it, locating a new location for it, and abandoning it and drilling a replacement well. And that's a conversation that we have quite a bit with clients is, well, hey, I'm going to spend 10, 20, 50, 100, $200,000 on a rehabilitation plan, or do I take that and invest it into a brand new well? And you may not ever be able to regain that lost performance. So there is some significant risk in the decision making. So what you look at the history, if you do the performance monitoring and tracking, it helps you make that decision about, hey, this well has been a problem for years. Let's just move on and drill something new that's maybe more efficient, larger capacity, and stop wasting some of your money. Smart use of your resources. But we would come in and diagnose it. We would look at, okay, well, how have you been operating it? How much have you maintained it? What have you been doing? Have you noticed any problems over time? And if you have, what sort of maintenance history have you done on it? We would look at how the well is constructed. Is the seal intact? Is that contributing to some of your biofouling? Are you getting some surface water contaminants and pathogens that are making their way and then establishing themselves in the well bore? Or was it just poor development from the drilling contractor? Normally when you drill the well, it damages the borehole walls. It creates the skin. And so you need to go in and develop that well and reestablish that hydraulic connection. And if the development was never done, that can contribute to a loss in performance over time, especially if the wells were drilled mud. They didn't really have a good mud program to get rid of that, and there was some residual mud left behind. You've sort of set the tone for the well not to be able to meet sort of its expected life performance. You've started at a lower level than you otherwise would if it was constructed and developed properly.
You're referring to driller's mud, correct?
Yes, driller's mud. Yep, that's right. Yeah, and oftentimes they'll use mud to hydrostatic pressure to float the cuttings up, keep the walls open, opposed to drilling and driving casing, because that can be time consuming and expensive. So we'll do a pumping test. We'll look at the performance. We'll monitor. We'll take a static water level. We'll turn the pump on. We'll track the production rate and the pumping water level. We'll look at specific capacity during that period. And, depending on what sort of history that water purveyor has, we can compare that recent specific capacity or well performance or result to when the well was first drilled or when it was last rehabbed. And you can sort of get an idea of, okay, well, how's this well been functioning? Is it exhibited some performance declines for a long time, or how far are we off or away from its baseline performance or what you would normally expect from this well? We would track some other pumping system parameters to see where we are on the curve. Is it a pumping problem? And this is all before we would even, crack open the well and do any in situ work. And then at some point, you may need to remove the pumping system and inspect it, do a video survey and see if there's any problems. Is there evidence of any biofouling? Can you see some silt or fines that are plugging up the slots in your well screen? That's all very, very informative. Has it filled up with sand or silt and it's blocking now 60% of your well screen? Let's go in and pump that out and clean it out and open up a little bit more open area for water to come in. And if we are seeing some evidence of any biological activity, let's take a groundwater quality sample and figure out, is it a physical plugging? Is it just silt, clay, residual drilling mud, or is it a biological plugging issue that would need to be addressed by a more targeted chemical rehabilitation program? So in developing the plan, you really look at your well type, know the condition of it. It could be an aggressive plan. In the case of, this was the city of Yelm in the Puget Sound area, we went to a much less aggressive approach. But the different sort of methods coarsely are mechanical rehabilitation. That's when you're just using a big brush to run through the length of the casing and scrub the inside of the well screen to break up some of that stuff that's a little harder to see. This is a really heavy duty wire brush. This is a little less abrasive wire brush. The bristles aren't as coarse. So there's different mechanical rehabilitations methods you can use. You can rawhide it, which is pumping the water up into the column and then shutting the pump off and letting that water fall back in if there's no check valve to, impart some energy into the formation and kind of break up and allow the water itself to break up any plugging that might be happening. Impulse generation is another technique that people are using. These are proprietary rehabilitation tools that can be used. Hydropulse or air shock is an example, and it's a tool that goes down the well and you can regulate the frequency and the magnitude of these bursts of nitrogen gas that help send out these big pressure pulses through the screen, through the filter pack, out into the formation to help break up some incrustation, loosen up some of the silt or clay that may be plugging it up. And oftentimes this is done in combination with some mechanical methods, and we'll oftentimes use some dispersants to help break up some of those fines as well. And it's important too to try to pump, if you can, pump simultaneously when you're doing this to remove some of the debris or the fines that you're creating. Otherwise, you're just pushing that stuff back out into the formation, and it's going to be more and more difficult to remove. So we highly recommend some simultaneous pumping, whether that's an airlift system or a submersible. That again kind of depends on how much space, how big the well is, how much space do you have to work with. And then there's chemical rehabilitation. If there's some microbes, some microbial contaminants that have established there, let's take a sample. Let's see if we can diagnose what sort of species they are, identify what would require to eradicate the population, whether that's just disinfectants or acids or biocides. What do we need that targets removal of those contaminants? And again, that's typically used in combination with some of the other methods. And expect and plan for change. Like I said, there's no silver bullet solution. Some wells respond really well, others don't, and it requires maybe several trips brushing through the entire screen column to really break it up and remove it. So performance monitoring while you're doing the rehabilitation is important so that you can track the relative improvements. So you do these specific capacity tests at the beginning, so you know how it's how it's performing now, and I can walk through the figure a little bit. That top little dotted line is kind of the baseline of specific capacity. That's how you would normally expect your well to perform. Well, you have a problem and you did your specific capacity test and you're way off the curve. You're way down here. So something's wrong. We need to develop a plan to try to restore that loss in performance. And by doing these tests sort of periodically through the rehabilitation plan, it lets you know where you are. Have you reached the performance that you would normally expect from the well, or you can use it to assess whether brushing and bailing and surging didn't work. We need to go through something more aggressive. And as you go through the plan, you can see relative improvements in your specific capacity, and it'll help you decide, okay, we may not be able to restore all of it. We've gotten close. We're at a point of diminishing returns. We could stay out here for months and keep doing this. At some point, we need to stop just because we can't afford it. It's working. Let's stop. And that becomes kind of your new baseline performance that you would use to track any sort of the need for any subsequent rehabilitation or restoration efforts. But it's important when doing those specific capacity tests to really be systematic about how you're doing them. It depends on both rate and time. So if you pump at 500 gallons per minute for 10 minutes opposed to 100 gallons per minute for an hour, it's going to give you very different specific capacity results. So to be able to compare apples to apples and really assess the relative improvement, it needs to be comparable to each test. So try to pump it at the same rate for the same duration each time so that you can compare them and get a better sense of the improvements. And then document and reference. There's a lot of times where we hear, yeah, the well hasn't been performing for a while. We'll go brush it and clean it. And we've done that a bunch of times, but they haven't documented. There's nothing we can go back on to really assess, okay, well, this worked and that didn't. So let's develop a plan that focuses on this and not that. Having that information is really beneficial. And then, wrapping up the recommendations, just know your well and your pumping systems. There's a lot of times where, 9 times out of the 10, purveyors don't know where their intakes are at. Even like what depth do they have them at? Are they in the well screen? Are they up shallow? And how vulnerable are you to groundwater level declines? Can you deepen your intake? We don't recommend putting the intake in the screen zone because that increases your fluid entrance velocities and causes more problems. Conduct routine inspections. Do a wire water efficiency test or pull the pumping system and do a well video if you can to see if there's any indications of any problems. Monitor and the system performance regularly. Once, great. 2 years, twice a year seasonally would be better. Hit those seasonal groundwater level highs and those seasonal lows. That'll give you some information over time on is the aquifer recharging to the static that we would normally expect to see this time of year, or we're seeing sort of consistent declines in your groundwater level from these summer fall measurements year to year to year that would tell you we might need to deepen this well or come up with some other solution to address any loss in your available drawdown. And then consider the age and the condition of the well when developing the plans. Keep them active, try not to keep them idle for too long. And then, keep that pumping water level above the top of the screen if you can. A lot of the times the purveyors will just pump as hard as they can. And what that does is, again, it creates higher fluid entrance velocities because you're utilizing less of the screen, and that water's coming in at a faster rate that could exacerbate existing problems. So that's all I have. I'll just wait for questions to the end and I'll turn it over to Dan.
Perfect. You could probably drive from
to John. All right.
Okay, so a lot of what we've talked about so far has been focused at the well and well field scale. I want to step back for just a couple minutes and talk about the long-term supply planning and a little more that comes a little more from a regional, resource protecting our aquifer kind of perspective because of the importance of that supply. And I was thinking about, again, why often are we asked to build models and what are people wanting to do with them? And when it comes to the stuff other than wells and well field optimizations, kind of boiled it down to really 2 big things. One is, and I think people in this region from, say the last 10 years, I've done some projects off and on over the years, you're all very aware of the externalities that influence the aquifer system. The aquifer sits inside a larger watershed. And years like 2015 came along, and now this one, where it's unusually dry, didn't get the big spring runoff. City of Spokane in particular in 2015, noticed some abnormally low water levels in their wells, and it kind of got them thinking, we need to take a little harder look at the resiliency of the supply we have relative to our hardware, but also to the aquifer itself. So we're tending to look a lot at climate change influences, which is not just kind of what classically hydrogeologists think about, which is, how does the rainfall and the stream flow affect the aquifer? I'm actually finding a lot of the work I'm doing these days, temperature is a big deal because it's changing customer water demands, therefore changing the way we're using wells and having to think about demand and supply management. And the models we build are being done to help guide decision-making and management. And then you superimpose growth influences like what all is happening here with just the tremendous growth that's going on. And what that means for what the demand profile looks like, how much, the seasonality of it, and how conservation should perhaps start fitting into that, maybe in a little different way than has been done in the past. And then the other thing, and this is a little more on the Washington side, there's certainly been, studies that we've done to help understand the relationship between the river and the aquifer during the low flow season. And that's because in Washington, there is a real dynamic and close coupling of those two systems. Just kind of a quick visual example of that latter point is right here from some work we did with some of the SAJB members last year, more just kind of, not last year, about 7 years ago, just kind of helping them think through and understand more from a hypothetical perspective, what if a water district had two wells, one kind of close to the river, one farther away. Let's say they're in the same pressure zone. Could they maybe use one a little more that's farther away from the river than they're accustomed to using and back off a little on the one close to the river during, say, the summer season when we're all concerned about low flows in the stream. And so we could do analyses where we model that idea of how to kind of geographically distribute the pumping and start looking at the results in a time sense of, what kind of percentage benefit during these peak seasons are we having, for every, let's say, 1 CFS of pumping, are we getting, in this case, about 50% of that 1 CFS is an increase in river flow. That's been kind of a helpful thing for some utilities to know. Now, I'm going to show something from the city of Spokane, a little bit related to that, but partly related to water quality. As probably most of you know, the electric well field over by Upriver Dams, it's very close to the river, big Caisson Wells, as Kenny showed some of the pictures of. We were involved in a study about 3 years ago where we did installed a couple test holes and started thinking about, would a vertical well field in this location make sense for the city? And the reason they were thinking about it was that when the flow in the Spokane River gets above a certain amount, I don't remember the exact number, it's either 15,000 CFS, they automatically have to turn off the well electric facility because of connection with the river and microparticulate concerns. So that means they can't use that well field at times and when they may want to. So we started doing some work to investigate whether a vertical well field might make sense. And we identified various sites that, you could maybe think about putting some wells, did a test well out there, and much to our surprise, and really got Dan and I super excited when we discovered this, was the aquifer wasn't quite as simple as we thought it was. Turned out there's a gravel unit like we all know and we're all used to seeing, but at that spot at least, you go down about 150 feet and there's a fairly thick sand unit down there. Very different characteristics. Still look to be pretty permeable. And we started thinking about, gosh, what could a well field look like? And we came up with some, sort of just a rough prototype design of how might you construct it, how deep might you, put the top of the well screen and the bottom of the well screen. And then we took our 3-layer groundwater model, carved it up into an 8-layer groundwater model so we could start thinking about screen depths in some detail, and then started using the model to say, okay, if you pumped that well field and or the Caisson wells in various ways, where does the model think that water might be coming from? So tracing the actual groundwater flow paths to the well. And what you're seeing on the left is a view where those yellow particles are showing where the water is getting to the Caisson Wells, which in this particular model, the yellow color meant they're staying up in that shallow gravel unit and they're pulling water, partly from the river. But that well field down in kind of that lower right and lower center area where all those other different colors are, the model was saying if you're screening down that deep, there's a good chance you're pulling water from a completely different direction. You're not pulling it from near the river. And if it is going to intercept river water, it's going to intercept it somewhere off that map, some distance away. And the plot on the right was just a cross-sectional view of the same thing, showing that, in the white, the shallow Caisson wells, basically all their flow paths are staying shallow, but the deep wells, all their flow paths are staying deep until, somewhere, maybe here in Idaho, who knows, they become shallow. So this got the city pretty excited. And of course, the one thing you all have to do is remember it's a model, right? So one of my earliest mentors, who was a groundwater modeler, kept saying, now, John, if you believe your models to the 15th decimal point, we're going to have to send you to Modelers Anonymous. Remember, there's always uncertainty in these things. And what helped us feel like we were onto something was that we had some data out here in those test monitoring wells, where in the green line, what we're plotting on this plot is groundwater elevations on that left vertical axis and showing what they are for a well, the monitoring well in the deep sand in green, the shallow gravel in orange. And you can see that the groundwater levels are about 2 feet higher at all times. This was over about a 2-month monitoring period that also coincided with when the river was coming down off the spring freshet and starting to stabilize, to something lower. So both units were tracking what the river was doing, but we have an upward gradient is this is telling us, is water from that deep zone wants to move into the shallow pressure zone, which means that deep zone is pressurized, which means it's pressurized from somewhere distant away, kind of verifying the idea that we might not be, very real indication we might not be anywhere near this river in terms of hydraulic connection if they were to do a vertical well field. So very exciting finding. Kind of related to all that, then you start thinking about, the condition of the aquifer, on a long-term basis. Everywhere in the West, people want to, and aquifer managers, water utility managers, really kind of want to know, what does climate change potentially look like? And for those of you who are at the River Forum in 2016, you may remember some slides I'm showing here where we did some work to look at the data from the snow tell stations from 1980 through 2015. And we asked ourselves, gosh, what if you were to group the pre-2000 data in one group and the post-2000 data in another group, and start plotting up the frequency of various snowfall amounts for that first period versus the second period? Do they look alike or do they look different? And we developed something month by month that showed in December, the more recent period in orange, seemed to be shifted farther left, meaning, and the horizontal axis is how much snow there is. The vertical axis is the number of occurrences of that much snow. And it's a snow water equivalent is what we're measuring at the snow tell stations. You can see that more recent period, things were shifted towards less snowfall in orange than more snowfall in those earlier years in green. And if you just looked at that month by month through that whole data set, this was December, this was January, where you're seeing the snowpack building in both cases, continuing through March. But then in April, we're past the buildup of the snowpack. We do still see a shift of that orange versus the green, and certainly by May, even quite a shift as well. And when we thought about this information and thought about the long record of flows at downtown Spokane, which go back a long, long ways in time, you could actually see, if you looked just at the 1980 through 2015 flows, you could draw very similar curves between what the snow water equivalent in the watershed in April typically looks like and how it's varied over that 35-year period compared to what the flows in August in downtown Spokane looked like over 35 years. And there's some mathematical fitting to those data sets because they're noisy data sets, but they're you can actually tease out a relationship, and just the fact that you can do that makes a lot of sense, right? Because April snowpack in a large watershed, it makes sense it's going to continue having an effect all the way through the summer, and that's what this is saying. So that has implications for the groundwater system too, and so that gets you thinking about, okay, that was the past. What does the future look like? And there's all kinds of tools now to, of course, to start understanding that future. This is just one of them, the climate mapper tool. And this is just what they call a box plot that looks at April snow water equivalents for various periods of time. So in this case, 1971 to 2000, 2010 to 2039, 2040 to 2069, and 2070 to 2099, looking at a whole ensemble of various climate models and what they say future snowpack in April might look like. That's snowpack on the vertical axis. So from 35 inches down to about 12 and a half. And you know, you can see they're predicting a change, both in a case of where there's moderate future warming, what they call low future emissions, and then certainly in the case where there's high future emissions. And the tool also allows you to think about this kind of stuff spatially, where again, if you map out the highest snowfall amounts, snow water equivalent, I should say, on April 1st through this region historically, then looking into the future, and then looking way out into the future, you know, we can see some real differences as time goes on, which has implications for water management, including conservation, which Dan is going to talk about next.
Cool. I know, my apologies, I know we're running a little bit long here, but I just kind of wanted to talk about a couple of things that, and I think I jumped on my soapbox at the last meeting and talked a little bit about water conservation because it is something that's near and dear to my heart. But as you can tell from both John and Kenny's presentation, that there's avenues in which before we drill new wells, you know, maybe rehabilitating or using modeling to, you know, see how better to, if we do get to a new well scenario, where best to look to maybe lessen our footprint whenever possible. But certainly rehabbing well makes a lot of sense in the relationship of drilling another well and going through all that process. So go ahead. Wait for just a minute. This we got just a little, there it is. This is a really cool site. John gave me a call a few weeks back and pointed me to this. It's drought.gov. Just Google it and it'll take you to the site. It creates a beautiful interactive map. But, you know, this is what we've been faced with. You know, when I know Governor Inslee in Washington made a drought declaration in April, I was like, what? I'd never heard of a drought declaration in April. And then you look at what we're seeing today, this D4 categorized drought that exists today. And then I think it's the next slide kind of shows where we're at sort of stream flow wise throughout our region as well. And again, this drought.gov, it has various different filters on the left that you can apply and it'll take you to other maps to different locations. But what we're seeing here is that all of the flows that flows in out of our watershed to feed our aquifer system are either low or, you know, below normal in just about everything that's feeding into this right now. And we can overlay that same thing with change the opacity on that drought monitor. And it really starts to paint that picture of what that D4 area looks like when it starts to overlay with some of those challenges that we have in the stream flow. So all of those yellow dots are well below normal stream flows, and some of the red dots are below normal as well. So it starts to paint a pretty drastic picture, just not only what Terry faced, with his pumping issues, trying to meet demand during this type of a drought period. There's probably reasons for that. I mean, when we got rain in Spokane, I'm sure it rained over here a little bit on Sunday. That rain probably didn't really, penetrate soils much. I mean, it was probably gone and evaporated before, you put your head on your pillow that night. It's just, we're in such a soil moisture deficit that's been created by not only this drought, but again, looking at some of the snowtail data and seeing some of those diminished snowpacks, even though we were at 95% snowpack, how that came off, it really didn't have a lot of time to slowly migrate, infiltrate, recharge like you normally would see. We went from, anyone recall the last time it was 110 degrees in June? It's been a minute.
90s into May.
Yeah, right, exactly. Yeah, those shoulder seasons continue to seem to want to grow on us and not in a good way. So, the only method that we have available, and I know conversations with your customers is tough, but trying to take and look at a regional approach to conservation, and as I mentioned about the soil moisture, this drought.us or drought.gov site, they're also in partnership with NASA, so they're actually using satellite technology to look at soil moisture content, and this is the 100-centimeter slice of where we're at with soil moisture. And I think when I did this was earlier in the week, August 5th. So it's real-time data that you see from this site. Well, we're less than 2%, under 2% of soil moisture content, 100 centimeters of soil. So it begins to paint that picture that anything that may fall isn't really going to do anything in the realm of recharge or put much of anything and flow into any rivers or local streams or lakes. So most of that's just going to hit the soil and be gone in no time. So what do we look at? I mean, how do we begin to have that conversation around conservation that works on a regional level? And I think, it needs to be socially acceptable. I think that people need to get their heads wrapped around the idea that, this is a path forward. It doesn't have to be, totally stop, curtail everything all at once, but how do we begin to begin that message that it has a social benefit, it has a net ecological benefit both to wildlife, stream flow, your aquatic folks, fish like kind of like water a little bit, and water that's not 80 degrees. We were talking to someone last night, and they mentioned that behind the impoundment at one of the dams on the Snake, and water temperatures at 72 degrees. Not a lot of steelhead like that, and that hits me right in the heart right there. But there's also that piece of capital cost avoidance, and I think that when we look at conservation, and one of the things I did to look at conservation was jump on everybody's website to see what they had to maybe give me some pointers of direction, and I was really just kind of dismayed that there wasn't much out there in the world of websites that spoke much about conservation. I mean, there's a few sites. Terry's got some information on his website, and I think Whitworth had some. I don't know if Shane had a little bit on.
Just a little bit of stuff that goes to, yeah.
Yeah, but all in all, there wasn't really any consistent messaging. And I think really looking at that, that's kind of one of the things that we thought IWAC together for, was looking at that regional approach on how we can address some of those difficult conversations. And when they originally did the camp studies, Terry, you recall, that was 2012, 2013, and their population, their growth projections and their climate projections are way off base. You look at growth today, and I was telling Kenny and John when we were headed up Ramsey Road. We went up to another meeting earlier and, I said, this used to be fields. And you can't really distinguish Coeur d'Alene from Hayden Lake anymore, just driving down the road. You have to look for the road sign now to find out where you are. But having that ability to kind of come back and reset the clock and say, okay, now what are we really looking at? How do we look at this from both maybe a demand forecast model regionally, and then applying that regional consortium or group approach. I mentioned earlier, probably a previous meeting, that there's a gal with GSI, Suzanne, that had done a consortium of sorts on the mid coast of Oregon, and where a group of purveyors got together because they needed to validate their water use before they could get any more water right. It's kind of how things kind of, so I get that pretty close?
Yeah.
Okay. That's kind of how Oregon rolls, a little bit different than what we're accustomed to up here, but the same thing. I think one of the struggles is how do we convey that message to our customer? Because everyone looks at the Pacific Northwest and says, abundant resources, why conserve? Why do anything? And I think before we start to begin to drill new wells, because maybe our aquifer has dropped 2 or 3 feet, which can be the end all be all for some systems. I mean, most purveyors drill deep enough. They never drill, down to a depth that they have that built-in resiliency there. So, that aquifer level and make sure it remains static is pretty important. So how do we get this together and maximize those efforts with that regional approach? And by doing so, developing that emergency response and resiliency kind of footprint as well. And there's a lot of things that, we've done with the city of Spokane, with other water utilities in the Warren agreement, and ID Warren does the same thing on here, but is there piece and parts that would fit in this, regional plan as well? Because I think one of the biggest struggles to message this is that there's people that are very interested in conservation. There are people that they understand conservation, but unless it really impacts them fiscally, then we're okay. Right. And we know that if we want to raise rates, we're going to see conservation. But then we have the politicians come in and say, you're not doing that to my constituents. And I've been down that battle before. It's not a fun one. But being able to have that conversation to say, well, if we can avoid some capital costs and incorporate perhaps, a leak detection in a conservation plan, it may become more sellable. I was telling Kenny, we did that flyover by Utilis, they did the satellite leak detection. And, we had a Spokane has a leak detection program in place, and they have, folks going out there every day to look for leaks, but it's kind of like throwing darts at the wall. There's no dartboard. And that's what that Utilis flyover really did, was allowed us to throw at a dartboard. And then if you have, just a few folks that could go out and look at those leaks or investigate those leaks, you're actually making some progress and some gains. So I think, when we look at conservation efforts here, maybe it's not what it looks like on the west side or in Oregon. Maybe it's, what we need to do here to be successful with purveyors both on the Washington and Idaho side. So I think that there's a lot of good opportunities there. But I think what we really struggle with right now is, what are we looking at conservation wise? Because we know that our demand forecast and some of that data is just, it's out of date. It was a little underestimated. Expected to see the type of growth that especially Coeur d'Alene's seen in the last 2 years. So anyway, I just kind of wanted to get that blurb out and kind of.
One of the issues that I've run into is getting a consistent and whole story out to the customers.
Right.
Rely on the public news. I made that mistake this year. Oh my God, the sky's falling, the aquifer's drying up.
Yeah.
Too much growth.
Yeah.
None of it was true. I did a 5-minute interview with them. 10 seconds of it was used in
it's
cast painting the dire picture.
It's always the sensationalism that sells, right? So You know, in that mid-coast model that Suzanne put together was that consistent messaging and customer outreach. And it's not just bill stuffers or website updates or things like that, but it's actually, you know, you can develop that communication package that gets to your customer. And maybe it is bill stuffers, or maybe it is a newsletter that gets mailed out occasionally. But, you know, but you do need to get something in front of your customer. Maybe they might line the birdcage with it. I don't know. But, you know, in some respects, what we've done in the past hasn't really worked. So continuing to do it again, that's the definition of insanity, right? So, you know, trying a different approach, a different way of outreach, a different method of outreach, having that combined regional approach, I think is probably, you know, the next evolution of how we have to get to our customers and get in front of them.